You do? Wait, for track. Yeah. Why do you have? Yes, I know that. Yeah, you better. Oh,
I did have it. Oh, you guys need friends, yeah.
Wait, what's that?
Likes. Wait, say that again. You hear how you said that? Oh, yeah.
I'm the opposite. Hello?
Hi. Yeah. Hi.
Hello?
Hi. I
Hello?
don't know, but it's pie.
His name is.
It's on the first one.
What?
Stage. I'll stay. Yeah. For this week.
I'm done. Okay.
Yeah.
Yeah, I suppose we should get started. Assuming this will let me. The Lecture 22 review session tonight. For those of you interested, either I will be in Marshall Hall. I will prop open, they might like the doors by 7 o'clock, but I'll prop open the quad side if you want to get in that way. The rest you can join, come and go as you want, either in person or online. I ask you to bring questions that we can work through. So I'll stay in probably 102 from 7 to 9 tonight. This week we'll continue on with lactating cow rations. Exam is Wednesday. Any questions related to that? We'll stop at the end of macro minerals in lecture 20. We won't have any micro minerals on this test. Any questions? Okay, so we'll finish up minerals today, probably get started on vitamins. And we're coming down to the end of the semester here, so I'm not sure what Brittany's going to be able to do for the dry matters this week. So we've talked about microminerals. You got your quizzes back. You know what you need to think about, what you need to sort through for. Any questions on macrominerals? Microminerals, we've gone through the ones that you're generally going to supplement with a trace mineral salt. The first 6 there: iron, zinc, iodine, selenium, copper, and cobalt. Those we definitely can show very quickly, very definitively, that there is a problem when we take those away, or if they don't have enough of them. We get down into molybdenum, manganese, chromium, and fluoride. We start to have questions as to whether or not these are required or not. There certainly have been studies showing that, yes, there makes a difference when these are present, but we're talking long-term longitudinal studies that have to deal with purified diets for multiple generations. So the fastest you can do that is with mice. So whatever of those contamination they have of those 4 minerals in there, they got to work out of the system over 3 generations. And then, okay, maybe we can show that they're not performing as well as they could without those. But in everyday situations, we're dealing with contamination. So this stuff you'll get just by living on the planet. You'll run into it. You'll get more than enough. These are not things we balance for, but they have been shown in certain circumstances to be required. So molybdenum appears to be a cofactor in enzymes, so we're finding it in certain parts of the body. Certain enzymes it seems to be associated with. So normally, just living on the planet, you'll get enough of that. Contamination throughout your diet. Again, these are very hard to definitively say that this is the problem. You're trying to make that molybdenum the most limiting nutrient for an animal, and that's really, really hard to do, especially if you're dealing with a purified diet. And ruminants, you're going to run into all kinds of trouble with that purified diet. So we see, okay, maybe the 3rd generation doesn't grow quite as well as it might. So it's a very vague, because it's so hard to pinpoint, because it's needed, if at all, in such low amounts. Manganese. Again, we see it maybe helps enzymes work a little bit better. If it's present, maybe things will happen. So manganese, we're looking at impaired growth for a shortage of that, skeletal abnormalities, poor reproduction, birth defects. Again, do you want to attribute these to manganese or something else? So you're getting very small amounts, if at all, required on a daily basis or every other day basis. Then we start to get kind of generic. They're just not doing as well as they might. And then in theory, if we add that manganese back, all those things will go away. If in fact that is the most limiting nutrient in the diets we produce. And again, with ruminants, that's hard to do, because you basically have to feed them purified forage. Either that forage has to be grown on a special medium that does not have manganese, or you're giving them cellulose, ground and fine. And I know a bunch of sheep that were not very happy that they weren't getting hay. Studying the effects of copper and zinc on pregnancy. So manganese, if anybody's seen that movie, we're alluding to a slight problem there. The skeletal abnormality, manganese might be before your time. Got a problem with birth defects, skeletal abnormations. So Man your knees. I have a structural abnormality. Somebody's different than everybody else. Manganese. Chromium. So there's a big hot craze in the late 90s that chromium was going to make us all immortal. We're not getting enough chromium in our diet. Normally that's contamination, but they were starting to add it to cold remedies. That didn't last very long. We generally disease zinc at the moment. So chromium is related to poor immune function. If we don't have enough chromium in the diet, there's a suggestion that's related to proper immune function. We take that away, we give that back. We have proper immune function restored. At least we hope. So again, you're probably looking at work that's been done in mice, lab rats, some way, shape, or form. Fluoride. We have trace amounts that are found in the teeth and bones. It can substitute in as that negative ion for the formation of the crystals that make our bones hard. So is it necessary? Is it required? Well, maybe not. It's there, but doesn't mean that if we take it away, it's going to cause problems. Usually the problem with fluoride or fluorine is excess, too much of it. And we start to get excess, we start to have bad things happening to the body. So we have fluoride in some of our water systems to help strengthen our teeth, fluoride in our toothpaste to help strengthen our teeth. But if we get too much, things start to fall apart and it becomes toxic very quickly. So it's not something we worry about, but there has been some suggestion that minimal amounts are helpful, but we don't generally balance. There's more than enough contamination in the forages, in the feedstuffs to get more than we need. Downwind from a nuclear power plant can be a problem. So good thing I have the fluoride, so we're going in that green direction for there. Helpful for teeth formation. Excess can be a problem, so too much fluoride does weird things to your teeth. So we need some fluorine, so enough helps, too much hurts. Get your teeth going. And then, as we mentioned before, there are a bunch that even less amounts, if at all, are required. Aluminum, I think, is the most, it's either aluminum or silicon, the most common element on the planet from an atom perspective. So you're going to get aluminum all over the place. Has anybody heard what the challenges with or suspected problems are with aluminum? Dementia, Alzheimer's. There seems to be a high concentration of aluminum in those diseased parts of the brain. So there was a time where everybody got rid of their aluminum frying pans. Went from cast iron to aluminum, and they said, uh-oh, we need to get rid of those. I'm not sure it made a difference or not, but that's the way the consumer wanted. Arsenic, we think of that more as a poison. Nickel certainly helps our forage crops, but generally we don't think of it as a required for animals. Silicon, tin, vanadium, who knows if they're really going to be needed. We're looking at contamination from the environment are at levels that would more than be adequate for the amounts that you could possibly need. So you're dealing with such small amounts that trying to get a purified diet and trying to show that taking it away causes problems and putting it back fixes those problems. These are things that probably nobody's ever going to chase. They're just not economically important enough. So toxic minerals, cadmium, fluorine in excess, lead, mercury, all in excess will cause huge problems with our animals. I had a friend of mine worked in a battery, making automotive battery plants that have weekly blood tests. And if your lead got up high enough, you got a forced vacation to fix that problem. That's a little bit more risk than I want to take, but I guess somebody's got to do it. So mercury, certainly a number of problems associated with that in the environment and that. So we're thinking about minerals. We need to think about how they're absorbed. And this is the big thing of people coming to your door. They're going to say, my mineral is more available, therefore you have to buy less of it, but I'm going to charge you the same amount or charge you by the amount absorbed. So we need to think about what they're suggesting and what might influence how minerals get absorbed. Minerals need to be broken down into individual atoms in solution before they can be brought across the gut wall. So what we care about and what we're dealing with when we're balancing is the need of the cow, and then there's an absorption coefficient. So we have to, the amount needed adjusted by the absorption coefficient is the amount that has to be fed. What we care about ultimately is what gets absorbed in the blood. So there was a lot of discussion in the new NRC about this. What were we going to use for coefficients? How are we going to account for how things get absorbed? Those coefficients have economic value. We know that we can get calcium from chalk. Chalk is mostly calcium, oxygen, but the absorption coefficient is only like 0.2, maybe 0.1, 10% or 20% might get absorbed. If we have that calcium in a biological form, we might get 80% absorption. So that influences how much we have to feed given the source and where it is. So as I mentioned, people coming to your driveway to sell you stuff, they're going to talk about, well, my mineral gets absorbed better, therefore my mineral is better. So you're not paying for something that would stay in the D fraction and pass all the way through the cow untouched. So is that financially useful to you? So sources are assigned an absorption coefficient. So when we deal with more advanced computer balancing programs, all the sources will have their individual coefficient. So calcium chloride would be more available because it goes into solution better than limestone calcium carbonate. So we'll have that absorption coefficient. You'll also call it bioavailability. How much, once consumed, will end up in the bloodstream. So the equation for that, we take the amount of a mineral consumed, we times it by its absorption coefficient or its bioavailability. What percentage of that particular source gets broken down, put into solution, and ultimately absorbed across the gut. So what we're concerned about is the amount absorbed there. So we have to back adjust our calcium, back adjust our phosphorus, all our minerals to make sure that we consume enough so that the amount absorbed is where we need to be. So bioavailability, what determines bioavailability? So first thing, is it present or absent? If it's not there, it can't be bioavailable. So is it present in the diet or is it absent? And then we get into chemistry. What is the oxidation state of that mineral? Like iron associated with rust is not available in the body. That has a higher oxidation state than the reduced form that we need to absorb. What is the solubility? How much goes into solution? Calcium is very low solubility in water. The electrolytes, on the other hand, have a really high solubility. So they're going to be much more bioavailable than the calcium. And then what is the regulation of movement in the body? Is there any? Everything tends to move down its concentration gradient by diffusion, by osmosis. The more regulation we have, the more control of where things are, perhaps the faster things move. So presence or absence is an intake effect. Did the cow consume it or not? Oxidation state, solubility, that has to do with the chemistry, what's happening inside the gut. That's called the lumen. So the inside of the intestines, the center of the tube, is called the lumen. The big opening thing that you stuck your arm in through the cannula, that's called the lumen. The lumen of the rumen. So what's going on there? The pH, the water content, all the other minerals that are present will determine the oxidation state, will determine the solubility of a given mineral at any given time. The regulation or movement through the body, that's a tissue effect. So if we have like selenium being concentrated in the liver or concentrated in the kidney, there's going to be a lower concentration at the gut. There's going to be a tendency for it to absorb faster. Whereas if we've got the electrolytes pretty much constant throughout the body, we won't have as much of a concentration gradient that will drive that movement into the body from the lumen. So how much gets absorbed? We can talk about broadly inorganic minerals versus organic minerals. Inorganic, there's no calcium or no carbon around them. So we're talking about pretty much minerals. You're looking at something that's 99% dry matter usually, ground up, hopefully fine enough that it can go into solution faster. If we can get a mineral somehow absorbed into a plant, surrounded by protein or something like that, those minerals generally are more available than the inorganic forms. And these are lately what you've been seeing going to farms. Well, my mineral pack is better than yours because it's an organic format. So next question you ask, so how does it compare? What are the bioavailability things there? How much do I have to pay to make this work? We also can call the organic form chelated. It's surrounded by a protein chelation, and that has to do usually with the protein forming a claw, and you have the atom of the mineral sitting there in between. So as that protein goes into the abomasum, the large intestines, it gets dissolved and then frees up that atom from the minerals into the solution. So should go into solution a little bit faster. Ionic is another way to look at this. They're usually free atoms floating singly in solution. We think of the electrolytes as a classic example of that. So chelated. We take a soluble mineral and we complex it with an amino acid or a protein. Selenium is a classic example. You're seeing that people are growing it in garlic and growing it in onions, trying to get it into an organic form that maybe you buy less selenium, but it's more bioavailable to the animal. You're getting less waste and maybe less selenium's buildup in the soil. For chelation, you're going to need two functional groups, and you're usually dealing with things that have two charges on them. So calcium, magnesium, 2 pluses on each case for that. So two functional groups capable of donating a pair of electrons to balance out that positive charge. So that's sort of how they develop a loose attraction to each other, how the protein holds that mineral in place. So you're forming almost a ring structure with the metal being one section of that circle, one section of that ring. The theory is that chelated sources are generally more bioavailable than inorganic sources. I think there are exceptions to that rule, but it's a fairly good rule to hold on to. So as a rule, chelateds are not degraded in the rumen. They might start to fall apart in the abomasum, but really where they get freed up is in the small intestine. Some are formed naturally in the rumen, where the things happening there will create chelation. There have been some studies out there where we'll feed chelated minerals versus inorganic. The results are not conclusive. We're comparing against like calcium oxide or magnesium sulfate versus a chelated form of calcium or magnesium. So the inorganic forms to the organic forms, they're not really conclusive, and that's because there's a certain amount of flexibility that if an animal needs more minerals, the bioavailability generally cheats up. If they don't need as much, they can suppress the absorption, particularly for something like calcium. Calcium, you get too much calcium in the body, you'll turn to stone. And I do mean that literally. Too much calcium in the body, overdo it with vitamin D, you will calcify the soft tissues. If your heart turns to bone, that's probably going to ruin your day. We're talking about ridiculously excessive amounts, but there's a certain amount of flexibility. It's not just one definitive number. So if somebody's trying to sell you chelated minerals and say these are better, they need to show you. Show me the research where your version, when accounting for bioavailability, gave me something better than the inorganic forms. Sometimes it's just cheaper to feed a little bit more inorganic and get the job done. One of the things we have to worry about with minerals, and we try with our balancing minerals to get them roughly right. We don't want to overdo it with any one mineral. So there's an old adage, at least in this country, if a little is good, more is better. Well, with minerals, that's not always the case. And we have interactions in minerals that can be a challenge. So where do the interactions occur? So they could occur out in the soil, out in the environment. Things are influencing whether things are available. Crass tetany sort of falls into those first two categories. Food and or drinks, depending on what we're eating. If we've got an acid solution, it's going to make the calcium less soluble. So has anybody here done, get their calcium from orange juice? If you take, calcium, or orange juice fortified with calcium. If you take those things there and you gently pour them out after sitting for a while, all the calcium's on the bottom. Because orange juice is more acidic than milk, it's going to be less soluble, it's going to precipitate out. Now, when they go to analyze it, part of the analysis procedure is we need to mix up our sample. And by mixing it up, getting it up into solution, it will be present and therefore accounted for an increase in calcium. But if you look down the bottom of those cartons, there's an awful lot of greeny stuff down there that probably shouldn't be there. GI, there's a lot of interactions that happen in the gastrointestinal tract. Some of these things are good, some of these things are bad. There's problems or challenges with the absorption cells that line the gut. There's challenges in the blood and the tissues that we mentioned, I think last week we talked about the bombing of the nuclear reactor in Ukraine. Did we mention that last week? So dealing with that interaction, they're giving everybody iodine pills to make sure that we don't get the iodine into the thyroid first and let the radioactive iodine not be absorbed. There are other things we can do to modify what might be absorbed and what might not. So everything in moderation, and this is the way my professor told me a long time ago, we get everything roughly right, especially with minerals, and that's because of this. So what do you see up there other than a mess? Minerals going around the outside. So you have most of the common ones that you'll find on Earth. And then we have connections between those minerals. Those are documented interactions that occur between the minerals. So we have their periodic table, their chemical abbreviations there. Got phosphorus, chromium. They're arranged so these lines aren't too crazy. And then down at the bottom explains what we're looking at. If the arrows aim at each other, so arrows pointing together, see if that makes sense. Yep. Arrows pointing at each other means there's a synergy. Something good happens between those two. If arrows pointed away from each other, we denote mutual mineral interference or antagonism. So if you've got a pair on the line that connects, like if we look like phosphorus and aluminum, they're pointed toward each other. So what does that tell you? There's some sort of synergy there. If they're pointed away, for example, lead and calcium, got it pointed away. There's an interference or an antagonism that we need to be worried about. So the people that really understand this stuff can use certain minerals to block the poisons of other minerals. If you're looking at arsenic, here, you can use iodine, selenium maybe to interfere with that if we've got arsenic poisoning. So noting those interactions, those are used to help with toxicity. So let's give some examples and let's focus on potassium. So potassium's a K down in our diagram. We're gonna look at potassium down there at the bottom and magnesium. So what do we see on that line? Potassium's got an arrow pointing to magnesium on that line. Does everybody see that? Take the line, we got that little arrow here, says that there's an interference. Potassium interferes with magnesium. Does anybody know what that leads to? That's tetany. So if we have too much potassium in our forage, that happens a lot on freshly fertilized stuff in the spring. Put that potash down. Maybe it grows a little bit too fast. Maybe there's some luxury absorption of that potassium. We get too much potassium intake. That's going to lead to magnesium problems. And those magnesium problems will lead to the convulsions associated with grass tetany. So grass tetany, a serious, often fatal metabolic disorder characterized by low levels of magnesium in the blood serum, also called grass staggers or wheat pasture poisoning. Primarily affects older nursing calves less than 2 months old, but can occur in young or dry cows or growing calves. Happens most frequently when cattle are grazing succulent, immature grass and often affects the best cows in the herd. So nitrogen fertilizer is going to reduce that magnesium availability. Also, soils that are high in potassium or aluminum seem to precipitate the case. So we need to be aware of that interaction. Then we have potassium and calcium. So what's happening here? So that's what? We got some problems that are interference. So we know that too much potassium in our dry cow diets will interfere with calcium metabolism. Moving that around, possibly absorption. They interact in a bad way, antagonistic. That's going to lead to milk fever. A bad interaction. So we got to get the potassium levels roughly right, the calcium levels roughly right in our dry cows to make sure that we get things taken care of. And we avoid that milk fever. So a one-way interaction, a two-way interaction. So low blood calcium, usually around calving, leads to a reduction in calcium in the muscles. That lack of calcium in the muscles prevents contractions from happening. 3 types of muscles we'll deal with: smooth muscle, skeletal muscle, heart muscle. Has anybody besides Mr. Hughes heard those differences before? Smooth muscle, cardiac muscle or heart muscle, skeletal muscle. So without calcium, muscles cannot contract. So what usually goes first with our cows is, well, I only got so much. I'm going to prioritize which muscles I'm going to focus on contracting. So what do you think's got the highest priority out of those 3? Heart. The heart stops contracting, it's going to ruin your day. So heart is the last thing to go, and usually cows don't get that far. They usually can recover. The second priority is skeletal muscle. Their ability to stand up, to walk. So what do we know about milk fever cows? That don't fully go down, become paralyzed, how do we know that they might be going in that direction, or what happens to them right after you treat them? Anybody witness that? Anybody treat for milk fever? A lot of shakiness. They can't control their skeletal muscle because they don't have enough calcium to remain stable. So the lowest priority is smooth muscle. So that gets wiped out first. By the time we have the animals shaking and or going down, we've lost smooth muscle function. We've lost skeletal. Hopefully she's going to be good enough to get through cardiac. Anybody know what smooth muscle controls? Digestive tract and the reproductive tract. So if we don't have contractions, we don't push out the fetal membranes, we get retained placenta. If we don't have contractions in the gut, get displaced abomasum. We get a backing up of our gut. We don't eat. Nothing's moving. There's no mixing. There's no fermentation. There's no rumination. All those things are happening before we see her physically go down. So we need to work with that. The last interaction we'll talk about is potassium and sodium. Potassium and sodium work together in the body in some really fantastic ways. It's the movement of potassium and sodium in concert that allows nerve impulses to happen. Calcium rushes out of the cell, sodium rushes in. That sends a signal down the nerve axon. So sodium, potassium, what do we know about where we find sodium? Inside? Nope. Outside the cell. Listen, potassium is inside the cell. Sodium is outside the cell. And that's by design. That interaction between the two as they move down their concentration gradients helps run the body. So we take advantage of those positive interactions and move through. So you interact in a useful way for nerve impulses, for nutrient absorption, for osmotic regulation, acid-base balance, all those things we talk about with electrolytes, interacting in a positive way. So moving over to vitamins, we got a few minutes, we'll get them started. So vitamins, what do you know about vitamins? Need them in small amounts. So these, from an amount basis, are the lowest amount that you're going to need in the body. So we're down even below microminerals for the amount of dry matter that has to come from vitamins each day. We're looking at fairly small. So what else about vitamins? Anything else that anybody knows about vitamins? Okay, hopefully we'll teach you something here. So vitamins comes from the 1800s when we were starting to realize there was something in the feed that really wasn't that big, but it seemed necessary. And some of the early work that sorted those things out, figured those things out, suggested that there were amines involved, nitrogen containing compounds. Some certainly are that way, but there are a bunch that are not. So when they were trying to figure things out, they knew there was something essential that was very hard, especially in the 1800s, to quantify. So what we've since come to know or figure out is that we're dealing with organic compounds that are available in smaller amounts or needed in small amounts. They're generally, broadly, metabolic regulators. They help processes go forward. They help make sure that everything is where it needs to be. Everything is processed the way it might be. So we know we need them in very small amounts, but they are indispensable. It's very quickly, you can show B vitamin deficiencies in less than a few days. They're cleared through the body so fast, but we need them to be there. And one of the things that happened, we noticed that certain things are associated with the fat and certain things are associated with the water. So we have, those of you that quiz bowl before, water, fat soluble vitamins, water soluble vitamins, was that part of your studying? Maybe, maybe not. At least some of the things I've proctored, we have the fat soluble versus the water soluble. Has anybody done any organic chemistry? So there's a thing called the set funnel. So you take a feed sample, you're going to put it in, and you're going to have two liquids. You're going to have the oil, and you're going to have water. So has anybody dealt with Italian dressing, vinegar and oil, right? You mix it up before you pour it out. If you let it sit long enough, what happens? Separates, the oil goes to the top because it's lighter, the water goes to the bottom. So if you take a feed sample, you put it in that set funnel, you shake it for a while, you'll find that certain things move or migrate or become associated with the oil fraction. Certain things become associated with the water fraction. What they found is if you went through and filtered it, took out everything you could see, that there was something soluble in the oil. Oil is fat, so fat soluble. And something was in the water, water soluble. So after they filtered everything, there was still something in solution that seemed to be vital for these animals to grow, to be happy, be healthy, reproduce. So if you want to get what's in the water, you open up the valve down here, everything drains out, and then you study what's in the water. If you want to get to the oil, you tilt this over and you slowly decant the oil off the top. Then you study what's there. They dried those things out. They found that there was just barely anything on the paper or the beaker, but there was something there that was necessary. So they started to go through these things. The first division is the oil versus the water. And then they started to say, okay, well, what do these things do? And they started saying something in here is related to this. So they started labeling by letters. A, B, C, D. We found certainly one A vitamin it turns out the B vitamins, the water soluble vitamins, were divided into all kinds of different subsets that we couldn't get apart back in the 1800s, but as we've gone forward, we figured out how to separate those. There were some things that when you're going through, E was redundant of something previous, so they went back to the original letter. So we've got up to D. So here's the list of vitamins we're going to discuss. The ones that most animals need to worry about. So we have the fat soluble A, D, E, and K. That's usually a pretty standard quiz bowl question. What are the fat soluble vitamins? Which ones do we usually worry about when we're feeding cows? A, D, and E. If you're looking at ruminant mineral packs, vitamin packs, the A, D, and E are usually the only ones we worry about. Everything else is manufactured in the rumen. So you've got K is in the rumen, all the B complex, choline to a point, and then vitamin C, which we need because we can't manufacture it. Everything after a month or so old in a cow can take care of it herself, but we'll still talk about when it's necessary for other animals. So A, D, and E, and if you do things right, those are pretty well taken care of. Vitamins usually taken care of, especially on nice green pasture in the summer. Your vitamins will taken care of. So we'll stop there and we'll work through them one at a time next time. Yes. As soon as you can get there, yeah. If you would pass that on to your classmates, I think I saw Jason. Well, I did see Jason. I think he understood that we need to meet up there. He's talking to Lane, or no, Isaac. And then the rest of everybody needs to get up there as soon as we can. I gotta go get the van and then we'll get on the road.
All right,
So-
do you have support for one more meeting for the schedule?
No,
All right,
when were you were tomorrow morning sometime, right?
I think so, either
Okay.
tomorrow or Thursday.
Thinking it's tomorrow mornings.
Is
Does
it
it need to? No, it's not. I don't know where the hell it went. I know I had it.
All
I
right,
was trying to find it this morning and I couldn't.
all right,
So you want me to email you
yeah,
with that?
if you can,
I can do that.
all right, thank
So,
you.
Yes,
We're supposed to go to, we need to reprint an ID.
there should be signs for that.
Thank you.
I think it's to the, if you're standing out in front of Hamilton, I think it's to the right.
Thank you.
Yeah, I have to get over there and get, I've been told my ID doesn't work after 13 years. I need another one.
Left mine at home. It's cheaper to pay to replace it than to drive back.
Yes, it is.